All right. We're in section 7.3 where we're using functions involving what is called the natural base e. Um, and also is called what's called Euler's number. Um, One thing you have to keep in mind, the term e is a number. It's kind of like if you talk about pi, pi is like 3.14 or something. Well, e is an actual value. It's like 2.718, dot, 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 goes on forever. So, um, how it is used, you can treat it a lot like a variable, and also you can treat it like a number, depending on how um, they ask you to solve it. So when in the examples, it, when we're solving for natural base e, when we're asked to simplify, that means we want to leave the e in its natural state. We want to leave it as e to the something. So it's almost like you treat it like a variable, like you treat it like x. So the same rules still apply when you're using exponents. So if I had e to the 7th times e to the 4th, and I'm simplifying it, means I still want e there, but I'm going to use my rules for variables, which means I'm just going to add the exponents together, so it makes it e to the 11th power. For b, I got 24 e to the 12th divided by 8 e to the 7th, which means that 24 divided by 8 is 3. And then I got e, but then I'm going to use the quotient property, stating that if I have two variables of the same base, I'm just going to subtract the exponents. So 12 minus 12 minus 7 gives me 5. So then that's the answer for the simplified expression. For c, you're going to attach the square to both the 7 and your e to the 4th, so this becomes 49 e, and you get to multiply using the power rule. So that's 8. Now, if you were to um, evaluate, that means you're going to punch it in your calculator. So if I had something like this on my calculator, this one here, and I turn my calculator on like this, I think I already did it once. So if I hit my second button, and you see where it says natural log, but it has that e to the x power there, when I click on that, that'll give me like e to some power. That's where if I were to go like to the first power, I would get that 2.7 number. So if I'm looking for e to the 7th, I just type in the 7th, hit enter, and I get 90, what is it, 1096.63, and I want to go to the nearest hundredth, so let's go 196.63. If I were to punch in my calculator, 13 e to the negative 2 gives me something about 1.76. And if I punched in 17 e to the 2/3 power, I would get 33.11. I'll do example C on the calculator. So like what I did first was I went to E and I did it to the 2/3 power divided by 3 power, and I got a value, and then I multiplied it by 17 to get 30 there, 33 right there. Okay. Um, when we're dealing with the natural base E, it still shows up in some cases as exponential growth and exponential decay. The one fine difference is that if our value in the exponent is positive, then it's going to show it's going to show a growth. If it's negative, then it's going to show a decay. So nothing else changes. So if I were to look at these examples here, for example A, since I have a -3 in the exponent, I'm going to say that this is going to be a decay. And then since this is positive, it's going to be a growth. Okay? When graphing the natural base functions, you're still going to look for those key points. You're going to go to look for 0, comma a. The next one here is you're going to go 1, comma a times e to the r. Now I want you to evaluate this particular number. I don't want to have e on there because when you're graphing it, you want to have a value attached to it. And then you can round up the appropriate decimal point. And then you got -1 to the a over a times 1 over e to the r. So for example, a, I got 0, comma, my a will be 4. And then, so I got 1, comma, so it's what? A times e to the r power, that gets me about 6.6, I'll say. And then the -1, where it's a, which is 4, times 1 over e to the r is 0.5, and that's what, something about 2.43. So if I were to plot these points, I got 0, comma 4. I have 1, comma 6.6, so this is 4, that's 5, 6. I would say something right about there. And then I got -1, and then 2. So I got 2, and I'll say something like this. And I connect the points. So again, that validates that my exponent is positive, so we are doing an exponential growth. If I did have to put in, so if I put in the domain and range here, I would say the domain is all real numbers, and then my range would be y is greater than 0. Okay. If I had a transition pieces where I had a value for h and k. Here I have h equals -2 and my k equals -2. But the first thing I want to do is I want to plot the points for y equals e to the -1.5x. I want to plot points to that using the 3 points that the 3 key points that we talked about in not just this section but previous sections prior. And then once I plot those points, then I do the transition points. So if I just concentrate on this function, I figure out that my first point is going to be 0, comma 1. Second one is going to be 1, comma 0.22, and then the last one's going to be -1, comma 4.5, we'll say, roughly. So if I were to plot these points, I would have 0, 1. I'd have 1.22, so I'd say it's right about there, and then -1, comma 4 was a 1, 2, 3, 4. So I got 1, 2, 3, 4, so 4.5. So if I were to change the color, we've stated that it's going to shift to the left 2, so 1, 2, and then to down. This is going to be -4. I'm sorry. So it's going to be 1, 2, and then 1, 2, 3, 4. So that's that one plotted there. And I got 1, 2, 1, 2, 3, 4. And then I got 1, 2, 1, 2, 3, 4. So then it looks kind of something like this. My domain here will be all real numbers. My range will be y must be greater than -4. And that's where our k will help us with that, with our range. So lastly, we have a formula that's called continually compounded interest, where the equation is, or the formula is, a equals p times e to the r times t, where p is our principal amount, r is our annual interest rate, and t is time in years. So for example, if we're given If I deposited $3,000 into an account that pays 3.5% interest or annual interest compoundly continually, what is the balance after 3 years? So if I have A, my P would be 3,000. So then I got E, and then I have R, which is my annual interest rate, but we have to write it as a decimal. So it's 0 or 0.035 multiplied by 3 because T is 3. So again, we want to evaluate this because we want E to be the number. And so if I were to punch this into my calculator, I would get something roughly 3,332.13. So $3,332.13. And that is being able to solve for the natural base E. Hope this helps. Till next time.